All right, this is 2018. Number 5 it was a buffer problem. Number 6 was a electrochem problem, and so those are, I don't have those videos up. This is 2018 number 7. This is the last one. National average is 2, exactly 2.0 on this thing. Little photoelectron spectroscopy. Man, dial in, because there's nothing super complicated about your understanding of this stuff. It's easy questions to ask. These are the things that we hope for when we open up the FRQs. And so this says this is the complete photoelectron spectrum. So this is the whole thing. The first question just says identify the element. Easy enough. If it's the whole thing, the highest binding energy belongs to the 1s. So that's 1s2. After 1s2, that next little peak is your 2s2. And so each of those first 2 peaks held 2 electrons, which means this last peak that's here must hold 3 electrons because it's a little taller. And so that guy is going to be 2p3. And so there's kind of the label on those peaks if it helps you to label them. And so we're looking for the thing that has 2, 4, 5, 6, 7 electrons. Identify the element. Easy enough. The element's nitrogen, because it has 7 electrons there total. It doesn't say identify an ion, it says an element. That means it's neutral. Good? Easy enough. Then part B says this radioactive isotope of the element decays in half-life of 10 minutes. Calculate the value of K. How do you do it without knowing the formula? You don't. So you gotta dial in and know this formula. It's on the formula sheet. It's the very last one on the formula sheet on one side of it. The formula is K equals the 0.693. That's a constant when it's a first order reaction. Radioactive decay is a first order reaction. So looks this way. K equals 0.693 divided by the time for a half-life. And so they gave us the half-life of 10 minutes. So K is going to equal 0.693 divided by 10 minutes. And we can do that without a calculator. You need the answer, 0.0693. It says include units with your answer. That's an important piece of this because the second point in the middle of the problem is just for the unit. So if this is a first order reaction, then the way we determine what goes on the bottom of the K value, it's always just a number on top. We hold up the number of the overall order, and then we take that away. That means we have 0 molarities on bottom. So this is just 0.693 over the time unit. The time unit here is minutes. That's our K value. We get 2 points for that. So we're up to 3 points already. Then part C says, if 64 atoms of the radioactive isotope are originally present, what is the expected amount of time that will pass until only 1 atom of the isotope remains? So we have to get our 64 atoms down to 1 atom. They want to know how long that takes. Man, the simple way, the way I would teach it initially, is to say, okay, well, if I wait one half-life, then I've got 32 atoms left. That's my first half-life. If I wait 2 half-lives, I've got 16 atoms left. If I have 3 half-lives, I've got 8. Fourth half-life is 4. Fifth half-life is 2. And then my 6th half-life gets me to 1. So I've got 1, 2, 3, 4, 5, 6 half-lives that it took to go from 64 atoms to 1 atom. And so that is the work to show how you did that. And then you would take and go 6 half-lives. Each of those half-lives is 10 minutes. And so that equals 60 minutes of time. That's what they really want, right? What's the amount of time? Show how you arrived at the answer. 60 minutes. You're a winner. So the College Board justifies it that way. You can, look, because it's first order, you can fall back on your natural log. You can do natural log of the final concentration here. We'll call it A final, I think that's how they write it on the formula sheet, equals negative KT plus natural log of the original there. And so the final would be natural log of 1. That equal negative. We know the K value here. The K value is the 0.0693 over minutes times the time plus natural log of the 64 original atoms we had. Concentration or parentheses, doesn't matter. And you could do it this way, and you could plug those values in. I don't know why you would force yourself to use a natural log, but if you get jammed up, I always tell people, you get jammed up, you know this is a first order reaction, fall back on that generic equation like this and plug in the numbers you know and see if you can't figure it out. That time value there will also give us the 60 minutes if you went in and plugged those values in. So you could do it that way. And that's it. That's your fourth point. Your fourth point is coming up for the 60 minutes with either one of these kinds of work there. Short little problem at the end.